Hello everyone, my name is Yunuo Chen. I'm a PhD student at UCLA. I'm excited to present our new paper, a unified Newton barrier method for multibody dynamics. This is joint work with Minchen Li, Lei Hao Su, Yang, and Chenfanfu Jiang. Today, I will first give a brief introduction to the background and related work that our simulator is based on. Then I will talk in details about the core part of multibody simulation, articulation constraints with restitution control. Finally, I will demonstrate the ability of our system by showing some real-world examples. Let's start with background and related work. Multibody simulation plays an important role in graphics and robotics. Our overall goal is to present a multibody simulator with automatic coupling of rigid bodies and codimensional deformable bodies, high-quality results without artifacts such as interpenetrations, guaranteed algorithmic convergence, and strong numerical stability. Finally, reliable parameter tuning and restitution control. Multibody dynamics has been extensively studied in graphics. The key challenge is always on how to appropriately handle the contact among objects. Previous works are mostly based on the LCP method, which can lead to interpenetration in contact-rich scenes. To resolve this issue, we developed our simulator based on the Incremental Potential Contact (IPC) model proposed in 2020. IPC ensures accurate resolution of contact and friction with guaranteed non-interpenetration, strong numerical stability, and controllable parameters. Later in 2021, IPC was extended to simulate codimensional objects, including cloths and rods. The core ingredients of IPC is to formulate the simulation step as an optimization problem. The objective energy, called incremental potential, consists of inertia, elasticity, and an extra contact term to enforce contact constraints. More specifically, we calculate the unsigned distance between each contact pair and apply a smoothly clamped barrier energy to prevent it from getting to zero. Finally, the optimization problem is solved to local minimum using Newton's method with line search, which gives guaranteed global convergence. More recently, a fine-body dynamics (ABD) was introduced to incorporate rigid objects into IPC framework. ABD inherited robust and accurate contact handling from IPC and significantly reduced the global degree of freedoms for linear solving to achieve faster performance. The basic idea behind ABD is to embed the whole body into a single linear finite element. Here, the bottle will move along the affine transformation of the triangle frame. This gives 6 degrees of freedoms in total per body in 2D and 12 degrees of freedoms in 3D. Rigidity is enforced through elasticity by adding a single elasticity potential per body with high stiffness to account for the deformation of the linear affine space. In conclusion, we base our multibody simulator on the following energy expression. Using ABD formulation, we can unify the treatment for both rigid and elastic bodies in one set of degree of freedoms. For incremental potential, we consider inertia energy, elasticity energy, and contact energy based on the IPC formulation. Lastly, we add extra energy terms to address the articulation constraints. We'll discuss this shortly. Now we introduce the core part of our simulator, formulation of articulation constraints. Our articulation constraints include point connection, which allows us to conveniently simulate, a triple rod pendulum, and a cloth hanging on a coat rack, without the need to generate possibly non-manifold meshes with complex topology. We suppose the sliding constraints to force an object to slide on the other, letting us to simulate a three-section monocular without modeling the complex interior tunnel structures. Similarly, we can apply hinge constraints to simulate boards rotating around a shared shaft. Here, different rotation limits are imposed on each hinge. A nunchaku can be simulated with counterweight constraints, with rotation limits applied separately for bending and twisting modes. We summarize our articulation constraints in three categories: linear equality constraints, nonlinear equality constraints, inequality constraints. We'll provide a special treatment for each category. For the simple linear equality constraints, we apply change of variables to exactly enforce them, while for the other nonlinear equality and inequality constraints, we apply stiff penalty and barrier potentials to enforce them. Now let's discuss in details. Our linear equality constraints include point connection, simply enforce two nodes to be equal. Hinge constraints, construct by adding 2 points connections on the hinge axis. Contwist, to enable flexible control of rotations in each direction, we design a joint with 3 virtual boxes, connected one by one with hinge constraints. For example, box 1, 2, 3 controls the bending around z-axis, bending around y-axis, and the rotation around x-axis, respectively. To exactly enforce the linear equality constraints, we propose a change of variable method. We'll change the degree of freedom x to a new coordinate z, in which the constraints become zi equals si prime. Assume U is the transformation matrix between x and z. We can use chain rule to compute the gradient and Hessian matrix accordingly. The construction of U is carried out as following. Let the constraint Ci form a matrix C. We apply Gaussian elimination with row pivoting to get an upper triangular matrix C prime. Then we can form an upper triangular transformation matrix by inserting identity to the bottom right block. Nonlinear equality constraints Cx equals 0 can be enforced by adding a penalty term to the energy, with K being the stiffness parameter. Using this method, we can fix the distance between 2 points P1 and P2 to be L. We also provide the relative sliding constraint to fix the point P on a line segment of another object. This can be done by restricting the area of the triangle to be 0. Finally, to treat arbitrary inequality constraint Cx greater than 0, we extend the variable method used for contact to prevent Cx from approaching 0. We can simulate bounded distance between 2 points. We notice that other inequality constraints can be formulated as bounded distance. This includes sliding range. To restrict point P to be within line segment P1, P2, we use one additional point P3 on the extended line and express the range constraints with 2 inequalities. To restrict the rotation angle of point P within range theta min, theta max, we first rotate P to the endpoint Pmax and Pmin. Then P must be restricted on arc Pmax, Pmin. This can be further enforced by a distance constraint. Therefore, we can avoid computing angles by expressing the rotation range as bounded distance. One remaining issue of multibody dynamics is restitution control. This often appears in inelastic contact. For example, if we drop a ball on the ground, how high can it bounce back? Restitution also appears in inequality articulation constraints. Here, we have a vertical rod rotating around a red point. In 2D, after the rotation limit is reached, should the ball stick at the limit or bounce back? Since both our contact and articulation constraints are handled with barrier potentials in our framework, we thereby propose a general way to model restitution for both of them. With articulation and contact barrier potentials, the magnitude of bouncing back is directly related to energy conservation behaviors of the time integration. As we know, implicit Euler suffers from significant numerical damping. Therefore, we apply higher-order time integration methods like BDF2 to obtain significantly better energy behaviors. Here, we show that BDF2 let us conveniently simulate close to perfectly elastic restitution behaviors for both the contact and hinge constraints. For inelastic contact, we can simply add damping terms into the incremental potential. Here, we apply a semi-implicit Rayleigh damping model. With different damping stiffness Kd, different levels of inelastic restitution behaviors can be simulated in a controllable way. The same model directly works for hinge constraints. We just need to construct the Rayleigh damping energy using the hinge barrier potential. Our novel contributions together enable us to simulate complex real-world scenes in a robust and accurate manner. Here, we drop a ball onto a hanging bridge constructed by connecting 40 rigid bolts using 10 elastic rods. Here, we construct a pulley system with sliding constraints and point connections. Our simulator accurately captures the mechanism of this pulley system. When the right end of the rod is pulled all the way down, with smaller forces, the heavy box is lifted. We also handcrafted this pulley system in real world and measured the forces that keep objects with different masses static. Here in the left plot, the horizontal axis is the mass of the object, and the vertical axis is the drag force. Our simulation results match both the measured values and the analytical solution consistently, despite some measuring errors in the real-world experiment. Next, we simulate the closing process of an umbrella modeled by coupling a rigid skeleton with a cloth. The skeleton of the umbrella is composed of 13 rigid thin rods connecting to each other via point connection, hinge, and sliding constraints. Now we simulate a vehicle modeled with multiple rigid bodies. The vehicle is triggered by a cylinder engine connected to the back right wheel of the car, with all other wheels passive. As our simulation accurately resolves the frictional contact, the vehicle can navigate the terrain smoothly as we pull the piston with a constant force. With the unicycle rolling at different initial speeds, we simulate precession, an inertial effect only to be captured when accurate frictional contact and momentum conservation are resolved. Our method can simulate 60 ragdolls dropped onto the ground from random initial heights without any interpenetrations. Contwist constraints are applied here at each joint of the ragdoll with specific rotation ranges, imitating the mechanism of human bodies. Finally, we let the ragdoll take a break on a hanging bed formed by elastic rings and discrete elastic rods. We also cover it with a sheet to keep it warm. In summary, we present a robust multibody simulator with fully implicit nonlinear elastodynamics for rigid and deformable solids in arbitrary codimensional geometries. Our simulator guarantees non-interpenetration and algorithmic convergence, and supports a wide range of articulation constraints with general restitution model for both contact and articulation. Thank you all for your time and attention.